for everybody for coming today. I'm going to introduce you to a quick new integrity root cause analysis. I know it's a bit of dry subject, but I'll try to make it as painless as possible and as enjoyable as possible. I know it's a bit dry, but yeah, let's go with it. I'll start with a bit of story worth learning from. Columbia Space Shuttle, as we all know, that there was incident of Columbia Space Shuttle in 2003. 22 years of service, 27 successful mission, 125 million miles traveled. I wish my car could do so. How all that ended in that tragedy. NASA specifications suggest that there shouldn't be any foam shedding during the launch, but more than 65 missions at least showed foam shedding from the bipod ramp, which is actually the area where your shuttle is joined into your main rockets. It made them thought that they can actually, your shuttle is kind of immune to this foam shedding. And they had one near miss in Atlantis launch in 2002, just 1 year before, when more than 700 areas of damage were found, and luckily we didn't lose Atlantis. It landed safely. Unfortunately, it was not the case for the Columbia. January the 1st, 2003, we lose 7 best of the best NASA has ever produced. Coming back to our industry, are we doing the same? Are we learning from small incidents? Probably, we usually compare our industry with the rocket industry. We usually say that it's not really rocket science, but I still imagine why HSC is showing us every year that these many hydrocarbon leaks are out there in the North Sea. Coming back to our industry, we usually have small number of high consequence incidents. These are hydrocarbon leaks, and we usually we are quite good on investigating them. We most of the time conduct materials and corrosion study on those. Most of the time, we ignore the root cause behind that particular incident. Then comes the medium consequence incidents. They can be analyzed. They are usually analyzed. It all based on the operator operating that particular asset. Then comes the most important bit, according to me, is the large number of low criticality incidents, mostly not analyzed, and they usually point to system failure. Why I'm saying they're most important? Because you have got time, and there are so many of them, so that you can learn from them, and you can actually trend where your systems are and how they are performing. So, what I said, they are most important. Now, we know that we should be doing something about them. Now, we need to know about what we're actually looking at from the root cause analysis perspective. So the best example or best definition I've found so far from Bush and Paradis is that the most basic cause that can be reasonably identified and that management has got control to fix. It has got 3 major parts. Basic cause, why that thing happened. Reasonably identifiable, you can actually identify within a reasonable time frame. You shouldn't be taking 2 years to do basic root cause analysis. Then management should have control to fix. Basically, if you say operator's fault, you can't really fix it. Operators make mistakes. Why you should be doing it? You should be identifying how you're gonna basically train that person from the soft skills or hard skills. That's what should be done through the root cause analysis if you need to do. So what we have got out there are quite few open source, basic, I would say, root cause analysis. We are familiar with 5 why, usually used to ask 5 random questions. Why my production is not on, and do a bit of information on one of the example is Ishikawa diagram, which is that 6 bones going into a fishbone diagram, we call it. And there are some commercial softwares available out there. But the problem with them is mostly that they are trying to fit everything into one package, i.e. they become time and resource extensive. You're actually putting too much time to identify one root cause. You take 2 years to come to a conclusion when you have lost all this time to fix your system, basically. So what we are proposing, we got the idea from the Energy Institute guideline produced in 2005. that says that look at basically your corrosion and materials incident, then look at the design, look at the mitigation, look at inspection and operation, and then do basic analysis. What you're actually trying to do is basically establish basic mechanism, then gather relevant information, all that you have, and then further evaluate if there are any secondary cause, any underlying causes. Then if there is any problem with the mitigation, design mitigation, i.e. your chemical injection and your coating has got a fault, dig a bit further. And if you have got, when you do all that, just prepare one single page report. That's very important. That's good. For producing one page report, you shouldn't take long. So it's good for us. So what we were asked from the Energy Institute to develop our in-house system, we had our system in 2017-18, so 2016-18. We were asked to develop, basically, to build on our existing system. So the objective of this project, S1219, was to basically develop a tool with which one competent engineer that can complete integrity root cause analysis using consistent approach, and that should be achieved within relatively shorter period of time, i.e. less than a day. So it has got three major points. One competent engineer, ask me later who that can be. It has to be used as a consistent, they should be using a consistent approach so that you can actually compare apples for apples and oranges for oranges, rather than comparing everything in one lump sum. And then you should be doing it quick. That's the main point. How did we achieve that? We actually made 4 stages for the system. Very quick one, very easy, so that you can actually follow them easily. You don't have to babysit somebody for a longer period of time to actually tell them what to do. So 4 basic stages are immediate understanding. That's basically what you ask your offshore engineers. What happened? What's the line? Where it is? All that information is your immediate understanding of the event. Second is all the evidence collection. That's when you talk to somebody, you look at your procedure, you look at things, and then you come up with your evidence. Then you conduct the root cause analysis, which is easy part, and then you basically review it and report it at the end. So I'll go through these stages one by one and hopefully quickly, so that you don't get bored. And the first one is these 2 stages, immediate understanding of the event, which is quite easy, and you can actually identify that through your simple MCDRs, IQs, anomaly systems you have got already. So you come up with basic information, you collect evidence, and for that we have come up with one of the report template. These are 2 pages. To collect that information, you don't have to read it. It's too much text, I know. But what this one is showing you is the robustness of what it can prompt you to. So we came up with the forms that prompts you to collect X, Y, Z information. What it's trying to do actually there is basically get all the introduction to the event, then collect all the information about 4 Ps, paper, place, people, and processes. Once you collect all that information, you summarize it, you put it in here, and then you do or conduct root cause analysis. To do that, we have got a framework made for it, which actually shows you the basic technical causes. These are the causes you actually identify through all these materials and corrosion analysis. You actually look at something and you just go, design is not right. Nah, that's easy. Always we come up with, design is not good. People who did work before us, they did a good job there. Mitigation was, we were not putting corrosion inhibitor inspection. We didn't do good inspection, things like that. So these are the easy ones. We usually get that. The most important bit is, which we 90% of the time miss, is basically the processes. When you have got anomaly system, we really don't go back and see our anomaly system is working, yes or no. Our processes, inspection report coming back, are we reviewing them accordingly? And then look at the people and organization. Is the competence required for that particular system is available or not? Are we auditing it? So all that information need to be prompted. I'm showing you too much. But what it is showing you is that it's robust, technically robust. It's prompting you to identify a problem in areas where you want to. You don't have to read it because it's not out there. I can't really give you this because Energy Institute is producing this in 2 to 3 months' time, but I can assure you, if the people in front can confirm, that it can fit on one A3 page. It can fit on A3 page, and you can do basically tick boxes there, and it is readable. So what you do at the end of it, you need one report. Easy, quick, simple. So for that, we have produced a template. It's drop-down menu. You just basically click, put information next to it. I'm saying XYZ is root cause because of this. Mitigation didn't work because pump was not working. So simple. I'll show you one case study. We like case studies, don't we? Because it shows us that robustness of the system, if it works. So we asked Energy Institute to provide us some of the information, and the steering committee provided us with 3 or 4 examples. And we took one example which has already been tested and done quite properly. Quite few of you might recognize it, but I'll give you a simple preview of that. 2006, one of the Techlok Clamp failed. In 2010, that same thing happened, but on 1-inch gas lift line operating at 155 bar and 55 degrees Celsius. The materials and corrosion assessment told us that there was lack of heat treatment, i.e. resulting in martensitic structure, high hardness, and there was not much of the hardness checked, poor quality control during manufacturing. But interestingly, we identified that if in 2006 it could have been shared, strategy could have come out, and that could have been prohibited. So what we came up with the result through this root cause analysis, we came up with these numbers are actually the numbers on the flow chart, so that you can relate back to. You can compile that information for the system correction. But we came up with the obvious one, materials and application verification. Then strategy was not clear because the information was not shared. And the RBI was not aware that these kind of things are happening, so they couldn't do any sort of checks on them. And the most important one, which actually was appreciated by the operator, that corporate knowledge was not shared. Otherwise, it could have avoided repeat clamp failure. So in summary, what I'm trying to tell you today, that we have got or we are in process of developing one root cause analysis that can be used quickly, and that can show you different aspects of your small incidents. And that's easy because it's done through the framework and forms, and there is a guidance being produced for that. So these are not that many pages it looks like, but it's only about 12 pages that provide you guidance enough to do that. And that quick method is anticipated to identify root causes for the low consequence and high frequency incidents. What I'm trying to say, let's learn from low incidents. Thank you very much for your attention.